organizers and the staff of the Simons Institute for an excellent workshop and smoothly running and just great.
Hopefully that will induce them to turn the light on over the board. Sorry. It wasn't sure. Okay.
Next,
Thanks.
I think I have 20 minutes, and I probably only have 30 or 40 new concepts and problems to raise. So given all this excess time that I have the ability at time to tell you a little story. And the story is about how such a list of co-authors could have been assembled, and what could have happened to have 5 co-authors on this work. Amazing how they're all at the beginning of the alphabet, you know. With my name, I'm usually the last author, but I could have even been, I don't know. So actually the story is very connected with a bunch of our talks here. Steve Smale, I was a student here in 1964 to 67 in dynamics. And Steve Smale had been a topologist, and he turned the sphere inside out and proved the Poincare conjecture and got the Fields Medal. And shortly thereafter, he changed subjects. He did this many times in his life. And he changed subjects to dynamical systems. And he wrote a great paper. Everybody should read it, 1967, Bulletin in the American Math Society, about differential dynamical systems. And then a few years later, he changed subjects again, and he was studying economics. And he proved the theorem, the fundamental theorem of welfare economics, that there's a price system that clears the market, which was the subject of the talk. Was it this morning or yesterday? I'm so lost. I'm sure everybody's lost. So he proved this theorem, and I actually was at a conference once in England, and I saw he's presenting his theorem. And his theorem was by what he called the global Newton method, which was actually, you can now read this proof in Milner's topology from the differentiable viewpoint book. There's a proof of the Brouwer fixed point theorem in there. That proof of the Brouwer fixed point theorem can be turned into an algorithm. So that's Smale and Hirsch turned that proof into an algorithm, which they called global Newton. And they proved that the solution curves of global Newton always converge to an optimum. But here's this conference, and at the conference there's Scarf, he's got an algorithm, and there's Harold Kuhn from Princeton, he's got an algorithm, and Steve's got an algorithm, and how are you supposed to compare these algorithms? So now we have another change of subject. He becomes interested in how you judge complexity and efficiency of this disparate collection of algorithms that are now numerical algorithms. So Steve being Steve, he picks a very definite problem that's classical and oriented and of clear interest. And he says, let's do this one, and doing this one will tell us what the theory should be. And so what his problem was, the fundamental theorem of algebra. Given a complex polynomial, you're supposed to find a root. And he writes a paper again in 1981, Bulletin in the American Math Society, called the fundamental theorem of algebra. And at some point during that time, I visited Berkeley, and he asked me some questions, and I could help him and give him some ideas. And so I stayed vaguely interested in following his work there. And when he wrote the paper, I realized that the algorithm he had presented and the analysis he did, the upper bound estimate, was infinite average cost. So now he had a hook, he hooked me in, and we started working together. So then we found some finite average cost algorithms in one variable, and then Jim Renegar went and did n variables, and then we went and did n variables, and now, all these years later, here's Peter, and the problem is made a lot of progress, not yet quite solved on Smale's list, 17th problem, n variables. But there's kind of a transition, a natural transition. So, I used to work at IBM, and I had the impression there that it was a great job while it lasted. And I had the impression there that if anybody asked me a question, I'd have something to say about it. But this something might take me 20 years, which wasn't quite their business model. But even so, they were quite tolerant of me and treated me well, and I had a very good scientific life there. Sometime in this 20-year period that I was actually there, we had FOCM in Rio, 1997, and I called up Peter Lax and invited him to give a plenary talk at the Rio meeting, which he declined to do. But then we were sort of chatting about things. And he said, Mike, what have you been working on recently? I said, oh, various things in dynamics and complexity theory about solving systems of polynomial equations. And he said to me on the telephone, he said, well, if you were getting eigenvalues of matrices, that would interest me. So here we are 20 years later, and it's like IBM. And, in the meantime, there's a little work has progressed, and we've gotten a lot of information about the polynomial problem. And now maybe it's time to return to the eigenvalue problem, which, after all, ought to be easier to analyze. So then Diego Montano came to see me in Toronto. I was working in Toronto at the time. I wanted to be my graduate student. Suggested that Jean-Pierre and I share him as a student, and he work on this eigenvalue problem. So then he worked on the eigenvalue problem, but somehow he didn't finish the job. What can you do? You can't force your student to finish the job. They've been there enough time. They have to go. They have to get a job. They have children. Live a life. So he didn't quite finish the job. And so now it's a couple of years later. He didn't quite finish the job. So then we said, okay, we have to finish this job. And so Carlos Beltran and I was in Buenos Aires these years, and Diego's in Montevideo, so he could come across the river, and we spent some time together. So, okay, we're going to finish the job here. And Felipe and Peter, independently, in Berlin, so that they were going to finish the job, and unbeknownst to each other, we're both finishing this job. And so now there are two papers on the archive, which are about to be merged into one, which will be, I hope, better than either one of them, which will resolve this, prove some theorem. Yeah?
Just to add that we actually knew that each other, we were doing the same job, thanks to this workshop.
Yeah, we only learned
it wasn't the abstract.
Oh, yeah. Right. We didn't know. Even when we were here, Peter was down the hall and I was over there. We didn't know that. Anyway, so now we know, and so there's now 5 people involved, and a job that should have been finished by our graduate student some years back. And the whole subject is exactly what Peter described to you today. I don't have to. So the eigenvalue problem is, I'm going to take a matrix n by n complex, general n by n complex matrix, where you put a Gaussian on each independent, identically distributed Gaussians on all the entries of this matrix, and now you ask to find lambda and v, such that a of v minus lambda of v equals 0. So that's the problem, and the solution that we propose is you start with one that you know. Maybe let's find all the eigenvalues. So find them all. Let me just discuss that case for a while. All n of them. That's actually, this problem, in my mind, is a bilinear problem. It's not a quadratic problem. So to make it bilinear, a and lambda come together and v comes separately. And then the bilinear Bezout theorem gives you n as the number of roots. If you were to treat this as a quadratic system, you would be predicting 2 to the n roots, and in fact infinity would be a root, all of infinity would be a root of the problem, and it would be all degenerate. And since we don't want to deal with degenerate systems, we think about it as bilinear. Okay, and the solution of the problem is you take A0 with some lambda 0I and V0I, and then you take an A1 you want to solve, and you write down the homotopy. T equals, and we'll take the straight line homotopy, just for convenience sake. In fact, it's surely not the best one. So we take the straight line homotopy, T equals 1 minus T times A0 plus T times A1. And we continue the root. So the theorem is approximate zeros, approximate eigenvalue, eigenvector pairs are found with probability 1. These approximate are in the sense of Smale that Newton's method is going to converge. Approximate eigenvalues found with probability 1, and the cost and the average cost is polynomial in n.
Sorry, I gotta ask a stupid question.
I can't hear you. Speak louder.
I said, I'm sorry I have to ask a
Yeah.
stupid question,
Yeah.
but what's wrong with Gaussian elimination?
For eigenvalues, you find roots that way, but not eigenvalues. You find the solution. A Gaussian elimination is to find AX equals B.
Yeah.
Here we want to find the eigenvalues.
You can compute the roots of a characteristic polynomial.
You find-
Yeah. No, so I'm going to say a few things. Yeah, okay. Yeah. Plus one Gaussian elimination to find the characteristic polynomial. Yeah.
Exactly,
Yeah. Okay, so let me say several things. First thing is, most likely these continuation algorithms are not competitive with what numerical linear algebra people do. They have algorithms that work great in practice. Let me mention a few of them. One might be QR algorithm. I can tell you what, you take your matrix M and you write it as QR, and you write M as RQ, and then you iterate. And this matrix is supposed to converge to one that's upper triangular, and you read the eigenvalues down the diagonal. That's QR. Then you might have QR with shifts. With, maybe one was the Rayleigh quotient shift. I could tell you a story about that one too, but maybe I am getting short in time. Third one is the QR with Francis shift. And then a fourth one, compute the characteristic polynomial. Solve it. So let me point out that this one, for example, is an algorithm for the eigenvalues, but not the eigenvalue-eigenvector pair. So that may cause a problem, and I'll speak about that in a minute. So several things. This algorithm here, I would bet dollars to donuts. That used to be a good bet from the taker's point of view. Maybe a donut costs more than $1 these days. I would bet dollars to donuts that this algorithm is infinite average cost. It converges almost always, but I would bet it's infinite average cost. So this is the problem, that a lot of these algorithms will fail probably on some kind of surface of codimension 1 or a divisor or something. They'll fail, and the course will go to infinity as you approach this thing. The question is, what does that pole look like? When you integrate, you can have a pole, but is it going to be finite or is it going to be infinite? It's a delicate analysis. So I would bet this one is infinite average. Nothing's proven about it. That would be a good project for some student. This one fails for an open set of real matrices. So it certainly is, for the real matrices, is infinite average cost. So this is in general matrices. When the matrices are symmetric, these algorithms are great. This algorithm, it converges all the time and does it rapidly, but there's no complexity analysis. This one converges almost all the time, but I think it's an infinite average cost. This one fails on open sets of real matrices. It's unknown for complex matrices. Does it work for complex matrices with probability 1 or not? Unknown as far as I know. This one also unknown. This is a favorite one. And there's a very nice article by Batterson which will discusses this algorithm from a dynamics point of view. His article proves that, in fact, Wilkinson proved, and then Parlett proved for symmetric matrices that these algorithm works all the time. But for non-symmetric matrices, it fails. Here he proves for normal matrices, it works almost all the time, very few exceptions. This one, that's an interesting one. Trefethen's book, so you have to wonder, what did the numerical linear algebra people do? Trefethen says in his book on numerical linear algebra, never compute the characteristic polynomial. Never compute it. He says it is not backward stable. And then they always give this example of the Wilkinson polynomial, which is x minus 1 times x minus 2 up to x minus 20. And if you look at that as a matrix, it's 1, 2, 3, it's completely stable as a matrix for the eigenvalue, eigenvector problem even. But as a polynomial, when you write it out, if you change the some middle coefficient by 10 to the minus 15th or something, the eigenvalues become complex all over the plane. It's just a mess. So they say don't do it, that it doesn't give you the right answer. So actually, I think that's a very interesting question to explain this. From the point of view of condition of the problem as a matrix problem, as condition of the problem as a polynomial problem. So for example, I have to define what the condition of the matrix is. Let me do that now. So the condition of the matrix for the eigenvalue problem, so A lambda V, where A of V equals lambda V, then the condition number of this point on the solution variety is mu of A, lambda, and V is equal to the norm of the matrix project on V perp of lambda I minus A restricted to V perp. This is the Hermitian complement to V inverse. This is the condition number of the polynomial. You might wonder, we already had a condition number for polynomials, how this condition number compares to the condition number for the polynomial.
You want to multiply with the norm of A or not?
Yes, thank you. How does this condition number compare to the condition number of the polynomial? In fact, many of the matrices will be well conditioned. Some of them, like the companion matrix of the polynomial itself, will be as badly conditioned as the polynomial. I guess one would want to know what is like the average of the condition number in the fiber. I suppose the average will be a lot less, so that the eigenvalue problem with a given characteristic polynomial will be much more likely to be solved well by matrix techniques than reduction to the characteristic polynomial and solving that. Does that address your question? Okay, so what about this? This is a hay in a haystack problem. Well, not quite. So now that once you've made all these definitions, you just do what Peter did in his talk. You have to.
Thank you.
That's it. So there's nothing more for me to say. The theorem's on the board and the technique is as it was, except for a few more comments maybe. So let me see, what did I want to... I made myself a list. What did I put it in my pocket. What did I... Mathematical linear algebra, the straight line. By the way, the straight line homotopies are probably... Oh, there's another one. What is the Newton's method and what is the update? So I have 6 or 7 minutes. Maybe that's the most important thing I can say. We might ask, what are the best condition matrices from the point of view of summing this condition number squared over the different... Suppose I sum this over the eigenvalue eigenvector pairs. This is a function defined on the space of matrices. What's the smallest value? So it's at least n times the square root of 2. And I think we proved that the average on the unit sphere, in MNN is something like less than or equal to n cubed. So it's easy to find examples that are close to the mean, whereas in polynomial systems, that's a wide open problem. So Peter gave you an estimate of what the average condition number is, and then he gave you an example which is much, much worse than the average. And we don't know how to find one. Even in one variable, we don't know how to find good points that are polynomial in the average. Here in the eigenvalue problem, it's easy. You pick any old one. Or you put the eigenvalues down on the plane. This is not a hard problem to get close to the mean. But what is the best? It might be a lot better than this n cubed, because the lower bound that I know is n square root of 2. So that's one good open problem. And the second thing I did wanted to explain is something that these algorithms, of course, the estimates we do, are upper bound estimates. And so the algorithms that we exactly prescribe are very, very careful algorithms where we can keep track of everything that's happening. Practitioners wouldn't do that. And part of the problem of what we did goes back to what Steve Smale and I did, is what Newton's method we picked. So we actually picked the Newton's method that is not good from the perspective of implementation. And so let me just say what the difference is, so in case anybody actually ever looks at the algorithms we write down, they will see what not to do and how to change it. So suppose you have some parameter space like this, and you have your solution curve maybe like that. So now what Steve and I did, we said, okay, here's a parameter value. And let's just make believe we're actually on the curve, or we're close to the curve. We're right over here. Now we said, okay, let's increment this, and how much can we increment it? We'll have to, well, we have some method of telling you, and Peter and Felipe have some method of telling you how much to increment t to t plus delta t. And then what we say is we take this value itself and we use that for Newton's method at this new point. So we simply take the same value. Now, a much better implementation would be to take the tangent vector to this curve, which is anyway the Newton direction. So you're already computing it. So you take this tangent vector and move in the direction of the tangent vector. and use this point as your new starting point for Newton's method, you're surely going to be closer to the curve. Why didn't we do that? We didn't do that because this involves two computations. And in the estimates that we were doing, you had to compute this, and then you had to compute another inverse of the derivative at a new point. So you had to do that twice. And we didn't see that we got enough gain in the step that we could guarantee to justify the extra algebraic cost. So we only analyzed this algorithm. And certainly in practice, that's not the right thing to do. The right thing to do is maybe look at this whole line, do some kind of a search like they do in numerical methods. You maybe double your step size if it's working well, or half it if it's very difficult. Not to take a prescribed step, but to use the tangent to the curve and take a long step. So included in such a strategy is yet one more open problem, and that is, what's the average curvature of these curves in the solution variety? So for quadratic programming or linear programming, we saw the average curvature of the solution curves was small, and that could explain a long step method that would be much more efficient than any of the bounds. So that's the last problem. What's the average curvature of the solution curve? Average curvature. Maybe one could say something about that that would show that long step methods would perform much better in practice. Thank you.
Thank you for the nice results and the story. Any question?
Just I want to make sure that I understood correctly that this QR algorithm has guarantee of proof for the symmetric.
The QR algorithm for general matrices will converge to a, when the modulus of the eigenvalues are distinct, if all the moduli.
But I'm asking about the symmetric case. The symmetric case you said is...
I don't think QR in the symmetric case will do any better.
Oh, okay.
These things with shifts, the shifts are the fast ones, and the fast ones work in the symmetric case. There's a theorem, so they, almost every symmetric matrices, you put them in tridiagonal form, you do what you're supposed to do, and they converge. In fact, every point converges either to an eigenvector or to an angle bisector of two eigenvectors. So the method is great for symmetric matrices, but there's no complexity analysis done of it that I know. So, yeah.
No complexity.
Yeah.
Other questions? Okay, then we stop here. Thank you again.